So what we're interested in looking at now is the vector equation of a line. In 2 dimensions, the Cartesian equation's fine because you've got 2 pronumerals, you can make one the subject. When you move into 3 dimensions, of course, how do you push that through? So let's go back to 2 dimensions and just look at what's called the vector equation of a line. So here's a line, I've got 3 points on it, but now I'm going to draw in the position vectors for each of those points, and I'll just call them A, R and B. Now if R is on that same line as AB, then it must be true to say this, that the vector AR must be some multiple of the vector AB. Now, based on where I've placed R, it would be a fraction smaller than 1, but of course you could place R anywhere and it could be bigger than the length of AB and things like that. Well, we know a vector is head minus tail. So R minus A would be lambda times B minus A. Now if I make R the subject, so R I could place anywhere, I want an equation to find where is R on this line, then I'd get R is equal to A plus lambda times B minus A. That becomes what we call the vector equation of a line. But because now it's dimensionless, I can use that for 3 dimensions, I can use that for 4, 5, 6, whatever I like. So there's our vector equation of a line. Let's give A and B some coordinates there, x1, y1 and x2, y2. If I was to now write my vectors in column form, then the point that I'm trying to find would have coordinates xy. Where is it? Xy. And then it could be written as A, x1, y1 plus lambda, x2 minus x1 and so on. That would allow me to break it up and actually get some parametrics. We now have the parametric equation of a line, the parameter being lambda. I'm going to rewrite it this way though, as 2 things that both equal lambda. It's an unusual way of writing a line because normally we only see one equal sign. But that actually is the Cartesian equation of a line. And to prove it, I can do this. If I just play around with the first 2, do a cross multiplication, I can rearrange that and we get our familiar point slope formula. So it is indeed the equation of a line. If I now get this question, they don't just say write the equation of a line, they're actually specifying write the vector equation of the line passing through these. Bang! There it is. Now how did I get it so quick? All I have to do is any point on the line. I can pick any point I like that lies on this line. Well, they've given me 2 points, so I said 3 minus 5, writing it as a column vector. Plus lambda, now that second thing is basically the direction vector. So it's like the slope, if you like. Well, the direction vector, head minus tail. So the y value is -5 minus 8 is 3, and 3 minus 2 is 5. So there's our x value and our y value for the direction vector. Of course, I could have just as easily written it this way. That is also a vector equation. So that's the thing with vector equations of a line. There's not one answer. There's lots of different vector equations of a line because you could pick any point you like that's on that line. Now, depending on which point you pick, you would end up with different values of lambda for different points. But notice this, the actual Cartesian equation of this line turns out to be that. Y equals 3/5 x minus 34 and 3. But here's the thing to note. Have a look at the direction vector and have a look at the slope of the line. They're very similar, but the only difference, of course, is we're used to seeing the slope as rise on run. So the y value would appear on top over the x value, but of course the vector we don't write that way. The vector has the x value on top and the y value on the bottom. So the direction vector, when we're talking about 2 dimensions, is pretty much the reciprocal of the slope. Now here's an interesting thing. We're in complex numbers and we said if we rotate 90 degrees it's the same as multiplying by I. Now imagine we've got our complex number and I'm writing it as a vector. Well, its direction vector would be run over rise rather than rise over run because it's like the reciprocal of the slope. If I was to multiply that by I, and so the first one now I'm thinking of it as a complex number, I would get run plus I rise, times that by I have I run minus rise. Put that back into vector form and I've got the minus the rise over the run. So in fact, AB is perpendicular to minus BA. These slopes would multiply together to give -1. But confirming that, if I was to use the dot product on those 2 things, well, A on B, dot product with minus B on A, would turn out to be 0. So yeah, They are indeed perpendicular to each other. Notice it doesn't say find the vector equation, it just says find a vector equation. Because I say there's an infinite number of possibilities depending on which point you pick. So I picked the point minus 2, 1. And then I'm going to say, well, it's plus lambda times the direction vector. Well, if I'm in 2 dimensions, I just need to work out the slope of this line, and the slope of this line's minus 2 on 5, but I know the direction vector is the reciprocal of that. So 5, negative 2, and there's a vector equation. So the first one, any point, I could have picked any point I liked. I just happened to pick that one. And then the other one, it looks like 1 over the slope. If I want to find the point of intersection of these two lines, the first one, I'm going to write it this way. You know, when I want to find points of intersection, it's usually easier for the point to pick either the x-intercept or the y-intercept, because it's going to make one of them equal to 0. So I've picked the y-intercept for this one. So negative 1 plus some multiple of the direction vector. Well, the slope for this one would be negative 2. So flip it, I've got 1 and negative 2. For the other one, because I picked the y-intercept for the first one, I picked the x-intercept for the second one. And I'll get 3, 0 plus some multiple. Now I use a different pronumeral because there's nothing to say those are going to be the same. And then 5 on negative 3 for the direction vector. We're trying to find the point of intersection. So if they meet, the x components must be the same. So reading across this one, because remember r is x, y, so x would be 0 plus 1 lambda, and in this one, x is 3 plus 5 mu. So there's my equation up there. But if I do the same for the y values, I'll get minus 1 minus 2 lambda is equal to negative 3 mu. Simultaneous equations, which shouldn't be a surprise really. That's how we do points of intersection. We use simultaneous equations, so we still are using simultaneous equations. But I end up with mu is negative 1. So I now know mu is negative 1 at the point of intersection. I can just substitute it back in, and 3, 0 minus 5, negative 3, and that would end up being the point negative 2, 3. Find the vector equation for the line joining these 2 points. Once we've done that, we're going to write parametrics for any point on the line, and then we're going to find where the line meets the parabola y equals x squared. Well, they've given me 2 points. I chose minus 1, 1. I could have just as easily have picked 4, 11, doesn't matter. And the slope between those two, when we use our slope formula, turns out to be 2. So the direction vector 1, 2 times some multiple. Because the other way you could get the slope is go head minus tail, but when you think about it, that's essentially the same as the slope formula, because y2 minus y1 over x2 minus x1. The parametrics then, I just read across. The x component would be minus 1 plus lambda. The y component 1 plus 2 lambda. Okay, we've done that. Hence, find the coordinates of the points where the line meets the parabola. Well, y equals x squared. I'll substitute in my parametric form. We just got to find lambda. Expand out. We get 2 possibilities for lambda. Kind of makes sense. If a line's going through a parabola, you're thinking it's going to meet it in 2 spots. Sub that back in, and I get my 2 points. For lambda equals 0, sub that into my parametrics, I get minus 1, 1. And for lambda equals 4, sub that in, I get 3, 9. There's the points of intersection. Here's one from a couple of years ago. L2 is passing through the point. They've given us a point. It's parallel to L1. Find the equation of the line in the form y equals mx plus c. Well, equation of the line, I need 2 things. I need a point, I need a slope. You've given me a point, and you've actually given me the slope as well, because we know parallel lines must have the same slope. And the direction vector then is 3, 2, which means my slope is 2/3. So all I'm doing is going, well, okay, well, y minus 5 is 2/3 x plus 6. So now let's push this idea through to 3 dimensions. So the equation of a line that passes through 2 points, it's the same formula. So let's say it'll work in any number of dimensions. Right. A is any point on that line, and what I've called B would be the direction vector of AB, whatever the direction vector is. So let's find the equation, vector equation, through these ones. Bang! I could pick either point. I chose 1, 2, 3. And then to work out the direction vector, I'm just going head minus tail. So I went 1 minus minus 2 is 3, so there's my x value. 2 minus 7, negative 5. 3 minus 4, negative 1. We have the equation. Cartesian equation. This goes back to that idea of writing everything equals to the parameter. There it is. What? Because remember, r is actually x, y, z. So what we're saying is x is 1 plus 3 lambda. If I make lambda the subject of that, I would get x minus 1 on 3. I'm saying y is equal to 2 minus 5 lambda. If I made lambda the subject of that, I get 2 minus y on 5. And finally, z would equal 3 minus lambda. Make lambda the subject of that, I get 3 minus z. Now, it's unusual for us to see two equal signs for a Cartesian equation of a line, but that's because we're dealing with 3 dimensions now. I mean, should we go to 4 dimensions, you'd end up with 4 things that are equal to each other. We're basically saying, what does that parameter, what does lambda equal? 2020 HSC question. So they gave us 2 lines, and we had to find the point of intersection of the 2 lines. Let's write out the components. We know that 3 plus lambda 1 must equal 3 minus 2 lambda 2. The x components must be equal. That one's nice, it just tells me lambda is minus 2 lambda 2. Now, reading across the y ones, minus 1 plus 2 lambda 1 is minus 6 plus lambda 2. Okay, but we just said that lambda 1 was equal to minus 2 lambda 2. I can substitute that in and I can now find lambda 2. But here's the thing, do they actually meet there? Because you've still now got a z coordinate. And you might have a situation where those lines are sitting on one plane and the other one's sitting on a totally different plane. They might not meet at all. So we need to have a look at the z component, and hopefully this will give us the same value. So z plus lambda 1 is equal to 2 plus lambda 2. And yes, we do get the same one. So that confirms, yeah, they are meeting. Both lines are meeting at the same point. So you need to substitute into that third component to confirm that yes, those lines intersect. But interestingly, in this question, I probably didn't need to, because they told us it has a point of intersection. That's sort of implied in the question, because they said find the point of intersection. So there must be one. And because I only came up with one possibility, then that must be the one. So possibly in the HSC, that particularly, you didn't need to go and confirm it. But just remember that, you really need to make sure, unless in the question they've told you, yeah, look, there's definitely a point. Go find it. Oh, of course, now we actually have to go and find the point. So lambda 2 is equal to 1. I can substitute that into the second one, and we get, well, I wrote it as a vector, position vector. I guess I should have written it as the point 1, negative 5, 5. Let's find the equation of the line that passes through this point and is parallel. So it's a similar sort of question we would see in 2 dimensions. It's just in 3 dimensions now. Find the equation of a line that passes through a point is parallel to another line. That's what we're doing here. Okay. 2 lines will be parallel. Now normally we would say if their slopes are the same. But what we're now going to say is if their direction vectors are scalar multiples of each other. Because each line will both go some constant times the direction vector, and the other one will go some constant times the direction vector, then it just needs to be a multiple of each other. It doesn't necessarily have to be the same, because you could always factorize a multiple out and make those direction vectors the same. Okay, well, if that's the case, I can now just write it down. Minus 2, 1, 4, and it's parallel to this vector. Well, if that's a position vector, then I know the direction vector and the position vector is going to be the same, so it'll be in the direction of 2, 1, negative 2. Parallels are nice. Perpendicular, a little bit more work. So find the vector equation of a line that passes through 0, 2, 3 and is perpendicular to this one. Now in 2 dimensions it was nice and easy because we could simply say, oh, that's all right, the 2 slopes multiply together to give negative 1, so one's the negative reciprocal of the other. But we're now dealing in 3 dimensions. We've got 3 components, so how do you say the negative reciprocal of something with 3 things? That doesn't work. So now we have to think about vectors. And we know two lines are perpendicular if the dot product of their direction vectors is equal to 0. That's how we'll find the direction vector. The direction vector of the line I'm looking for, I've just called ABC. I know the direction vector of the line they've given me is 1, negative 1, 4. So here we go. I know that A minus B plus 4C is equal to 0. So 0, 2, 3 is on the line. It's equal to lambda times ABC. But it will be equal to some multiple of 1 minus 1, 4. I just now need to work out values for A, B and C. Reading across the components, lambda A will equal mu. 2 plus lambda B will be minus. 3 plus lambda C will be 4 mu. So from there, well, I know that lambda A is equal to mu, so I can now say that 2 plus lambda B is minus lambda A. I get an expression for lambda, it's minus 2 on A plus B. And then for the next one, using the Z component, I end up with lambda is 3 on 4A minus C. So those two things must be equal. Whew. I now come up with another expression relating A, B and C together, which I can now solve simultaneously with the other one we had. And I end up with B is now 23C on 7. I can let C be any value I like, because remember it's going to be a scalar multiple. So I've just picked 7, mainly so the fraction works out nice, it cancelled, and I'll get that B is then 23, and then A I can work out by going back in, and eventually I've got the vector equation of the line. There's a bit more work there with perpendicular lines than parallel. If two lines have direction vectors B1 and B2. Okay? So what we're saying is they're going to be parallel if one of those direction vectors is a scalar multiple of the other's direction vector. Perpendicular if the dot product of those direction vectors is 0. But there's now a third possibility, and it's called skew lines. Skew lines are lines that are not parallel, but they don't intersect. And that's weird because we keep thinking that non-parallel lines must intersect, but now because we're dealing with 3 dimensions, again you got a situation where one line might be on one plane, one line might be on another plane parallel to it. So the lines don't necessarily intersect anymore. And that's what we call skew lines. They can still be parallel if they're in the same direction, but as soon as it's not parallel, we say, oh well, those lines are just skewed. They never meet, and they're not parallel either. So we're going to show that these two lines are indeed skewed lines. Basically what I've got to do is show that these lines do not intersect. I can see straight away they're not parallel because look at the direction vectors. One is 1, 1, 0 and the other is 1, 4, 5. There's no way I can make one the multiple of the other. So I certainly know they're not parallel. I have to work out that they don't actually intersect. Alright, well let's try and see the x components. We get 1 plus lambda is mu, 3 plus lambda would be 4 mu, minus 1 is 5 mu. If I equate 1 and 3 together, I end up with mu is minus 1/5, and so lambda is minus 6/5. If I equate 2 and 3 together, I get a different answer for lambda. It's not minus 6/5. So because I get a different value, then there is no point of intersection here. So no, they don't intersect. We know they're not parallel because we looked at the direction vectors. So these lines must be skewed. They are skewed. There's something to leave you with. Generosity knows no ends.